Hello students, Miss Slyman here live from the Istanbul airport with Jack and Andre. It's very exciting. Andre just informed me our flight is delayed. Fantastic. So I'm going to keep making your video here. Jack and Andre both say hi from afar. Okay, so I had left off thinking about the ways that lines and planes intersect, and now we're going to talk about distance from a point somewhere down to a plane. So we have our always distance we're going to use as the normal because that's going to be the shortest distance, the perpendicular. So if we have some point here, we need to make a line that goes through that point and is normal to the vector. So we'll use, normal to the plane. So we'll use the normal to the plane to create this line, and then we'll find the length of the segment that once we find the point where the line intersects the plane, then we'll find the total distance from here. So let's do it. All right, find the distance between the planes. So here's our plane in vector form. So we know that if we rewrite this plane, we've got two different direction vectors. So I'm going to give our plane equation to be r, any point on the plane, 7, 2, 4, one of the points on the plane, one direction, 6, 1, 0, that's the s direction, and then the t direction, 3, negative 1, 2. Okay, so if I want to find the normal, then I'm going to cross my two direction vectors. So I'm going to pause and do that. You should do the same. Okay, so I got that the normal is going to be 2, negative 9, negative 9. And we're going through this point here. So that tells me the direction of the line that goes through my point and my plane and is going to be perpendicular to the plane. So the equation of my line is going to be sum any point, given point on the line, plus 2, negative 9, negative 9. And I'm going to use lambda here since we've already used t over here. So now we know this line is going to be perpendicular to the plane and it's going to hit the plane at some point. So where my line hits the plane, these values are going to be equal because that's going to be my point on the plane. So I'm going to set those two things equal to each other and solve. Okay, so I went ahead and set each of the components equal to each other. So I have my x, y, z, and then I turned it into a system with all the coefficients on the left and all the constants on the right. And then I used polysimult to solve. Remember, use your calculators. There's no need to go through all the algebra of elimination and such to solve this. Go ahead and use polysimult. So what this tells me is that for these different values, that's going to give me my point on my line and the point on the plane, and those are going to be the same thing. So now I could go ahead and find the point on the plane by plugging in either lambda or the s and the t. If I plug in lambda here, that's going to give me my x, y, z on the plane. But again, what I really care about is finding the length of the distance in between that point on the plane and this point A. So really, I'm going to jump straight ahead to go from my point A to the point on the plane. I'll call the point on the plane P, and I'm going to find, I want to find the magnitude of AP. So first of all, finding AP, well, that's going to be plugging in my lambda, negative 1 plus 2 lambda, and then subtracting my A value. So my A is negative 1, 0, 2. So now when I subtract this negative 1, of course, what's going to happen is that the negative 1 cancels with the negative 1. So really, this whole AP is just going to end up being my lambda term. So I'll have negative 9 lambda, and I'll have negative 9 lambda. And then I want to find the magnitude of that. So I'm just going to put it in my calculator. You should too, and come back and see if we get the same thing. And you should get your length is about 1.81. Make go back and fix my symbol here. Okay, so that's to 3 significant figures. Calculate it yourself, make sure I got the right answer. So in your paper, there's something that talks about using the projection to find this with Cartesian form, but of course projections aren't in your syllabus anymore. And so instead we're just going to do the same thing that we did before. We're going to find this equation of the line that goes through the point, find the point of intersection, and then find our distance here. So knowing that we're going to have, if from Cartesian form, I can see my normal direction. So my normal direction is 2, -4, 7. And now here's my point. So I know that the equation of the line that's going to go through is going to be r equals 0.48 plus 2, -4, 7. And again, I'll use lambda. So this is the equation of this line. Now I want to know my point of intersection. So I've got my x, y, z values. I'm going to plug those into here to find out what lambda needs to be. So 2 times 0 plus 2 lambda minus 4 times 4 minus 4 lambda plus 7 times 8 plus 7 lambda is 10. I moved my 10 to the other side. And then you solve that, and you should end up with a lambda value of -10/23. And now I'm going to do the same thing. I want to find this distance here, so I'm going to come back, plug in my lambda. That's going to give me this point on my line. Once I have that point on my line, I want this distance, so I'm going from this point to the new point. All that's going to cancel. So I'm going to get that if we label some things here. So if we call our point up there Q, point on the plane P, then vector PQ is just going to be, I don't know why I put those brackets around that. PQ is going to be 2 lambda. Geez. Let's try that again. So 2 lambda, -20/23, and then -4 lambda, 132/23, and 114/23 to get our z coordinate. So there's our point of intersection, and if you calculate out what I just worked out, it does end up being the same as we got an autograph as the point of intersection. And now if we find the magnitude, you should end up with approximately 3.61 as autographed it as well. So same method, doesn't matter what form we're in, we're going to find the equation of the line that runs perpendicular to our plane, and then we're going to find where the line intersects the point. And in the end, I can use just the lambda part of my equation of the line to find the vector that connects the point to the line, and then find the magnitude of that resulting vector. So that's it for these notes. Hopefully they'll be uploaded sometime soon. The internet has been iffy here, and I'll see you back in class.